This is EE 619, lecture 16. So we have been looking at the linear delay model. We said that the absolute delay of a gate is now split into a unitless delay into the delay of the reference inverter. And this unitless delay D is given by P plus GH, where P is the parasitic delay. How do we calculate this? So the diffusion capacitance at the output divided by diffusion capacitance of an inverter with the same drive strength. Now G is the logical effort. How do we calculate this? This is the input capacitance of the gate divided by, so input capacitance of the inverter with the same drive strength. So either you do both these calculations assuming a unit device, or take into account that the inverter also needs to be upsized to match with the drive strength. And finally, you have H, which is the electrical effort. How do we calculate this? So the load capacitance divided by the input capacitance of the gate. So after yesterday's class, last class, I got some questions on whether the diffusion cap here needs to be accounted for the load capacitance. What is the answer? It shouldn't be accounted because the diffusion cap information is already captured into P. So this H deals with whatever fan out capacitance is there, right? You shouldn't count the output diffusion cap of the gate itself. Okay, so we solved the problem without this additional gate yesterday. And I had asked you how this table was going to change in the presence of this additional gate. So let's quickly look at that. So now in the presence of this additional NOR gate, what all values in this table are going to change? Which one? The load capacitance of I1. How does it change? So 10C plus the input capacitance of this stage, right, which is 10C. Right? What about the input capacitance of I2? Does it change? That doesn't change. So let me explain why. So for example, let us take a NOR2, which is sized at 1. This has a certain input capacitance C. Now, if I size this at K, this input capacitance is now going to be K times C. Now, let's say I have the same inverter. This is sized at 1, but I have connected it to some other logic here such that the input capacitance, the total capacitance here is now still equal to K times C. Okay, so I have connected some other logic here such that the total fan out capacitance is still K times C. So now in the second case, when the input capacitance is K times Cn, you also know that the drive strength offered is K times higher. The resistor here is going to be R by K, right? Whereas in this case, the resistance is still equal to R, right? So it is not benefiting us in any way and shouldn't be part of the equation of the Cn here. This is clear? This H, which is CL by Cn, also captures the information of gate sizing, because that is going to give you, if you upsize a gate, it is going to give you higher drive strength. So the H captures that information. So if you are increasing the Cin, it means that you have upsized your gate, correct? But just because you connected a load here, it is not offering you any benefit in terms of the drive strength, which is why you shouldn't change the Cin simply because you have an additional capacitance. Is this clear? Okay. So what else will change? In Cin and CL row, does any other value change? Nothing else changes. Your H will simply become twice of the previous value. G is remaining same, P is remaining same, and you can recalculate what is the new delay value for each stage and sum them up to find out the total delay of the path. Any questions on this? All right. So we also did this calculation where we had to drive a fixed load with any amount of inverters that you could do, right? Initially, we had one inverter driving a large capacitor. Then we put two inverters to drive the large capacitor, three inverters to drive the large capacitor, etc. And our conclusion was that we have two parameters that we can optimize. The first parameter is N, which is the number of stages. And the second parameter is the gate size. So first, we will now assume that your number of stages N is fixed. And then we will see what to do to obtain the optimal sizing. So now let me set up a sample problem on which we can do all this calculation. Let's say this is the total load that this path needs to drive, CL. And we are interested in optimizing the delay in this particular path. And for now, we will assume that the N is fixed in this particular sample problem. N is equal to 4. Now we know that the delay of each stage, let's say the kth stage, can be represented as Pk plus Gk into Hk. Okay, so assume that the NAND and NOR are two input gates. Now what I need to do is, I need to choose a variable, represent the delay of each of these stages in terms of that variable, then sum them up to find the total delay and figure out how to optimize it by changing the sizes of these gates. So now, what variable should I choose? The problem statement is clear, right? So I need to start all these calculations by choosing an appropriate variable. We are interested in sizing all these gates. So what variable should I start with? Size of each gate. So one suggestion is that I can use, let's say, size of each gate, alpha 1, alpha 2, alpha 3, etc. Is there any other suggestion? What is H of? H of each of the gates. Okay. Is there a better way to phrase it? I mean, all of you are in the right region. The size of the gate is actually a very good starting point to suggest, right? But if I choose the size of the gate, then I need to calculate the input and output capacitances of the gates. And that actually depends on the logic that I have implemented, right? Which means our delay equations are going to get slightly complicated. So a better variable to choose is the input capacitance of the gates. Okay, so let me put that. Let's say the input capacitance of the first stage is X0. For the second stage, it is X1. So this is X2 and X3. So let me write the expression, then it will become clear. Right? So now the delay of, so let me write the input cap of the kth stage is what? X k minus 1. Okay, which means the electrical effort of the kth stage is now xk divided by xk minus 1, right? Then I can write the delay of the kth stage as pk plus gk into xk by xk minus 1, which is still a very nice compact equation. So we have a very nice linear delay model, which is giving you clean and compact equations. But if you are not careful about choosing your variable, you can end up with complicated equations to solve, right? So if you had chosen the size, then you would have to calculate what x1, x2, etc. are in terms of the logic gate configuration and the size you have chosen. So this is a much easier way to go about the whole. Okay, so now our total delay is equal to summation of the decays. This is summation of all the pk plus summation of the gk into xk by xk minus 1. What comment can you make about the summation of the pks? This is constant, right? Once you know what are the logic gates that you require, and if the number of gates is fixed, it is not going to change. Doesn't depend on the sizing. So whatever you do, this number is a constant and will not change. So now if I want to minimize D, I should focus on minimizing this part. Okay. So I am now interested in minimizing summation of gk into hk, which is same as minimizing the stage efforts fk. Gk is also constant. I'll come to that. Okay. So far clear? The problem formulation is clear? So now I'm going to introduce few new parameters. So let's give a bench for the equation to wait. And then let me introduce what is called as the path electrical effort. This is represented by capital H. So what is the stage electrical effort? Electrical effort for a given stage? What is the definition? Load capacitance by input capacitance. So what should be path electrical effort? So the C out of the path divided by C in of the path. So in this particular case, it will be xn. So for us, xn is basically CL, right? So it will be CL by x0. Okay. Now let me also look at what I'll get if I take a product of all the FKs. So we are interested in minimizing the summation of FK. I'm defining a new parameter as product of all the FKs, right? So this is equal to product of all the GK and HKs, where K is going from 1 to N. This is a product. I can split this. So this is K going from 1 to N of all the GKs into K going from 1 to N of all the HKs. Now, this parameter is what we will call as the path logical effort. Okay. This will be represented by capital G. What do you think we should call this parameter? So let us look at that. What is product of all the HK? Yes. So this is H0, sorry, H1, H2, etc. up to Hn, right? So this is going to be X1 by X0 into, what is X2? X2 by X1 into X3 by X2 all the way till Xn by Xn minus 1. This is clear? Therefore, this is now basically equal to Xn by X0. all of this gets cancelled out. All the other terms will get cancelled out. And this is what we set as C out of the whole path divided by C in of the whole path. Now here is a question for you. In writing this set of equations, so from pi hk to this definition of path electrical effort, did I make any assumption? Let me give you a hint. In going from here to here, actually not from there to there, in going from here to here, did I make an assumption? N is fixed. Yeah, that is fine. There is no branching, right? So we'll discuss this point in detail, but in writing this, we have assumed that there is no branching happening. So if there is no branching happening, then the product of HKs will be equal to path electrical effort. So this is now equal to capital H. Okay, so now what can you tell me about the capital G for this particular problem, which is product of all the GKs? Once the logic is fixed, the GKs are fixed, therefore the product is also a constant. Right? What about capital H? So this is C out of the path divided by C in of the path. Right? So when you usually start, C out and C in will be fixed. There will be usually a constraint on how much input capacitance you can offer. Right? So this is also fixed. Which means now the product of the product of all the stage efforts, Fk, is a constant. And the product of the stage efforts, what should be represented using? Capital F, just by following the conventions that has been done so far. So the path effort, pi Fk, is a constant. Okay. So now let me bring back to the problem we were discussing. We were interested in minimizing summation of Fk. And I have also derived an expression for product of Fk. Summation of a sequence, product of a sequence, what does that remind you? Right. So let me explain. So this should remind you of both arithmetic mean and geometric mean. And we are going to use a result from there called as the AM-GM inequality. So let's say I have a sequence going from A0, A1, etc. up to A. What is the arithmetic mean of the sequence? Summation of all the A's upon N. What is the geometric mean of the sequence? So you take the product of all the AIs and take the nth root. And what is the inequality? AM? Is it less than? Sorry, AM will be greater than or equal to GM. And if I tell you that AM is equal to GM, what comment can you make about all the A's? They are all equal. So AM will be equal to GM when A0 equal to A1 equal to A. So now we are going to use this result here. Let me quickly calculate the AM and GM for our sequence of F. So what we have now is a sequence of F's going from F0 to Fn. So the AM is given by summation of all the Fk's divided by N. GM is given by product of all the Fk's raised to 1 by N. And the AM-GM inequality tells us that the sign has to be greater than or equal. Now we also know that this RHS is a constant, right? Which means what is the minimum value that the LHS can take? It has to be equal. So the minimum value for summation of Fk has to be equal to n times the product of all the fk's raised to 1 by n. And product of all the fk's is what we called as the capital F or the path F. Is this clear? So now under what condition do you get this? What comment can you make about all the fk's? They are equal. So all the fk's are equal. And the value of fk will be equal to, has to be f raised to 1 by n. So that's it. So now we know that the minimum value possible will be equal to whatever is the path parasitic effort or the path parasitic delay plus the minimum value of summation of fk, which is n times f raised to 1 by n. So take a minute and see if you have any confusion in the derivation. So if there is branching, instead of, so pi fk is still what you have to look at, right? Just that the pi fk will be equal to this pi gk into pi hk. So the derivation is still the same. The expression for capital F is pi fk, and that is not equal to g in h. So I'll come to that in a minute. So we take into account the branching by introducing an additional term. I'll explain that in a minute. But check if you have any doubts in this derivation. Now let us quickly look how things are going to change if we have branching in the path. Okay, so we'll again do this with a sample problem. Let's say this is driving another inverter, which is sized at 90. So what is the capacitance? 90 times 3C. This is also driving the same load, 90 times 3C. Let's say the path of interest is like this. I'm calling this as I1 and I'm calling this as I2. So now can you quickly construct the table for this? So we have I1 and I2. C in, C out or the load capacitance CL. Then we have H, G, F, and also calculate what is the value for capital H. What is the value if you take the product of all the HI, capital G and capital F. What is C in for I1? 5 into 3C. So I'll keep writing into 3C because it will nicely get cancelled. This is 5 into 3C. C in for I2, 15 into 3C. CL for I1. So it is 30 into 3C because you have another 15 into 3C coming from here. CL for I2 is 90 into 3C. What is H? Electrical effort given by CL by Cn, 6. So you get 6 for both places. Logical effort of an inverter, 1. And therefore the stage effort can be calculated as 6 and 6. Okay. The capital H is basically the total output capacitance of the path divided by the input capacitance. So that is 90 into 3C, this value, divided by the input of the path is here, which is 5 into 3C. How much do you get? 80. Now, what is product of all the HIs? 36. So you can clearly see that capital H is not same as product of all the HIs, right? So to account for this, we introduce another parameter called as the branching effort. So we can calculate this branching effort for each stage, and then the path branching effort given by B will be equal to product of this branching efforts. So the definition of B for a given stage is as follows. You look at the total capacitance there, which will be the capacitance that is on the path plus the capacitance that is going off the path, divided by the capacitance that is on path. Right? So for example, in this particular example, your path is like this. So the capacitance on the path is the capacitor here. Right? This is the branching path. So this capacitance is called as the C of path. So what is B for the first stage? So you're looking at the output of the first stage. The capacitance that that a particular stage has to drive. This is equal to 2. And this is equal to 1. There is nothing branching. So your total branching effort is now equal to 2. Right? And pi into HI is now given by your capital H into capital B. Okay. So your electrical effort, earlier this was just G into H. Now, sorry, the total path effort, earlier it was just G into H. Now it has to be GH times B. So if there is no branching happening, B will be equal to 1. And the rest of the optimization algorithm remains as it is because we derived it based on F and the number of stages. So the F expression now is GHB instead of just being GH. It's clear? Okay, good. So now let us try and make sense of the result we have had, right? So we are now required to drive a particular capacitance. And let's say you are required to keep minimum input capacitance, which means you will start with a unit-sized inverter. And you have some logic that you are using to drive this. Now, if you had no constraint, so if the constraint given to you is minimum area, how would you size these? Minimum sized. So all of these would be sized at unity, right? Now, what comment can you make about the stage effort of all of these stages then? Will not do. Minimum area is the constraint. If minimum area is the constraint, you start with all of them being 1. Right? Now, under this constraint, let us look at how the delay is going to perform. Right? So the stage effort for this inverter is going to be minimum possible because it is driving another minimum sized gate. Stage effort for the next stage is also minimum. This is minimum. But the last stage is now going to see a very large stage effort, right? Which is what was increasing your delay by a lot. So now you decide to reduce the stage effort on this, let's say by increasing this to something. So now the stage effort of the previous stage has also increased. Now all that our algorithm, optimization algorithm has told us is that you make sure to obtain minimum delay, the stage efforts are distributed equally. Instead of making, one gate drive the load by itself, you distribute the stage effort equally among all the stages. So the stage effort is now going to be, if capital F was the overall path effort, that raised to 1/4 at all stages. Same here also, right? And then you decide how to size it such that the stage effort of capital F raised to 1/n is obtained for all stages. Okay, so now we are in a position to do a very nice problem. So let me give you a circuit. So the first stage is a unit inverter I1, followed by a NOR gate I2. This is I3, and you have one more inverter I4. And this is driving a very large inverter sized at 36. So this is all to give you that the load you are driving is 36 into 3C. So constraint given to you is you have to drive a load which is sized at 36 into 3C. The first stage is sized at unity. How would you size all the other gates? This is the problem that you have to solve. Let me give you the steps that you need to follow. So step 1 is to find out what is the optimal stage effort. Which is F optimal. Now, step 2, you calculate the input capacitance of each stage. And step 3, based on these input capacitance, you calculate the gate sizing. Okay, so why don't you give it a go? So you are setting so F optimal will be equal to capital F raised to 1/n. These are not two inputs. So each Fk should now be equal to the optimal value of the F, which is F raised to 1/n. So n value is known to you, but you don't know what is capital F. So the first step is to calculate the capital F. So let me help you out a little bit. What should be the very first step? You have to start by assuming the input capacitance, right? So for the unit inverter, what is the input capacitance? 3C. Now for this stage, you assume a capacitance of, let's say, X1. This has an input capacitance of X2. And this has an input capacitance of X3. So you can build the whole table using these variables. What is the G for a NOR 2? Should be equal to 5 by the sizes are as follows. The total capacitance, input capacitance associated with the particular net is now going to be equal to 5C. So 5C by the input capacitance of the inverter, 3C, will give you 5 by 3. G for a NAND 2, 4 by 3, inverter has it. The parasitic delay of an inverter should be equal to 1. 3C by 3C. 2 and 1. So capital P, which is equal to summation of all the Pi, is directly equal to 6. Capital G, which is product of all the GIs, is equal to 20 by 9. Now capital H, which in our case is going to be same as the product of all the HIs because there is no branching. So you can directly write it as C out by C in for the path without actually having to write this row. That will be equal to 36 by 3. 36. 36 into 3C by 3C, which would be equal to 36. So what is your capital F? G into H, and this is equal to 80. What is the optimal value for F? 80 raised to 1 by 4. Calculate and tell me how much you get. 2.99, right? So we'll approximate it to 3. Okay. Any confusions in how this table is written? So if you were asked to calculate the minimum delay, you really don't have to write this line at all. You can directly calculate what the capital H is based on C out by C in for the entire path, and then calculate F, calculate the optimal F, and then you can write the delay information, right? What is the minimum delay possible? That is the path parasitic delay plus n times stage effort. And this is equal to, calculate and tell me what the value is. Should be equal to 80. It's so much clear. So now this particular row was necessary because we also have to decide on the gate sizing, right? That we are going to compute based on this. So the next step is to calculate the input capacitances. So let me help you with stage 1. This is the input capacitance. Input capacitance of I1 is completely known, right? So you can directly start with stage 2. So you can use the H of the previous stage to compute X1. So H of the previous stage, H1 is given by X1 by 3C. Now F1 is G1 into H1, and this we know is equal to 3. You know what is G1? You have the expression for H1. You can calculate what is X1. What do you get for X1? X1 should be equal to 9C. So similarly, repeat the calculation and find out what are the values of x2 and x3. So similarly, you can calculate the input capacitance for stage 3. So G2 into H2 is now equal to 3. You know what is the value of H2, you know what is the value of G2. Substitute and you should get your x2 value as, what do you get as x2? Should be equal to 81 by 5 times C. Right. Repeat the calculation and you can find out the input capacitance for stage 4. What is the value of x3? 729 by 20 into C. So do we need to solve for the last case? Do we need to check for G4 into H4? So you don't need to do that to find any parameter, but it is a good practice to solve it to see if you have made any mistakes, right? So if you substitute G4 into H4 based on the capacitance values you have derived, what do you get? It should be, you should get the value around as 2.96. Right? So we made an approximation. F opt was calculated as 2.99. We made it into 3. So the small numerical error is because of that approximation. But it is a good practice to always check this so that you can find out in case you made mistakes in your calculation. Any questions so far? So the final step remaining is to calculate the gate sizing. So your second stage is a NOR gate. Let's assume that this is sized at K. Then what is the input capacitance? Kc. It has to be 5 Kc, right? And you know that 5 Kc should be equal to, what is the value of X1 you calculated? X1 is 9C. So this should be equal to 9C. Therefore, the value of K is 9 by 5. Similarly, for the next stage, you have a NAND gate. What is the input capacitance? It will be 4C. Is this clear how I'm calculating the input capacitance? So let me quickly calculate the input capacitance for a NAND 2. So the sizes are 2, 2, and this is also 2 and 2. This is AB. This is AB. The total capacitance associated with the A is 2C plus 2C. So this gives you 4C. Now, if I size the gate by K, this becomes 4C times K. So 4Kc will be equal to, what should it be equal to? This is equal to the value of X2, which is 81 divided by 5C. So this gives you your K value approximately equal to 4. No, it is equal to, approximately equal. And then the last stage is an inverter, which we'll again assume is sized at K. Therefore, the input capacitance is 3 Kc. And 3 Kc should now be equal to 729 by 20 into C. So this will give you K equal to 12.15. Any questions here? So we started out with this whole problem. We found out that the minimum delay that is possible, what is the minimum delay possible? Is 80, right? And the sizes are, this is sized at 1. The second stage is sized at 9 by 5. What is the third stage sized at? This is sized at 4. And the last stage is sized at 12 points. Yeah, so roughly 12. Is the calculation clear? So now if I give you an output load to drive, and if I tell you that you have to drive it, you have to offer the minimum capacitance possible at the input path, which means you have to drive it with a unit inverter. You know how to design the gate sizes, right? Okay. So now let's say there was no constraint on the input capacitance that you need to offer, right? You are allowed to keep a very large sized inverter here, or the logic gates can be very large. Then how would you proceed with the calculation? So we did this calculation with the starting point as the input capacitance being 3C. So you are given that a large value of capacitance can be used there. Then how would you proceed? Capital H, so C in value is given to you, just that it is not unity, it is something very large. Okay, let's say a large value is given. It need not be unity, right? Then how would you start? So the C in value that you can offer is something very large. Okay, then how would you proceed is the question. Think about it. We can answer this question in the next class. Okay, so now let's say for the same problem, if the Cout value is much large. So far you were driving an inverter which was size 36 into 3C. The constraint comes on the part of the driver. So this driver is going to be designed by somebody else, or it's something that the customer is using from his end, right? So now that driver should be able to drive the input of your circuit in a reasonable time, right? So if you want to be very flexible as a designer, if you want your design to be used everywhere, you would want to offer the minimum capacitance possible, so that more number of any driver arrangement will be able to drive your path. Right? Now, in certain cases, maybe that constraint is not very strict, and the previous designer tells you that you can put a very large value of cap. So then how would you proceed with the question? If I increase the input capacitance, yeah. No, so if I have the option to increase the input capacitance here, I would also want to increase the input capacitance here. Like I will make the stage effort to be same. You can start from this side. So in this particular case, you had the option to verify your answer here because you had an extra equation, right? Now, in case Cn is not clearly defined as 3C, but some other value, then you have the option to start from the right side and back calculate. So that option is also. So if they have given you an upper limit, right, and you have the option to choose an X0 smaller than that, then you can do this. Okay, now for the same problem, so far you have been driving it with a inverter which is sized at 36. I'm telling you that now you need to drive it with an inverter sized very large, say 4500. Can you quickly tell me what is the minimum delay possible? This you should be able to tell me very quickly. Minimum delay possible is 10,000. What is 10,000? No, 10,000 is something related in the calculation. What is that? The minimum delay is 43. Okay, so let's quickly do the calculation. Now for the path, for the whole path, C out is equal to 4,500 into 3C. C in for the path is still the same. This is equal to 3C. Therefore, the electrical effort H is C out of the path divided by C in of the path, which gives you 4,500. The capital G, has it changed? The capital G has not changed. What is the value? So this is equal to 20/9. Therefore, the path effort is G into H. There is no branching. Therefore, the capital B value is always 1. And what is this value equal to? This is 10,000. Okay. So the minimum delay, D minimum, will be equal to the parasitic delay plus n times f raised to 1/4. What was the parasitic delay for the path? So this is 6 plus 4 times 10 power 4 raised to 1/4. 4 into 10. So this gives you 46. Okay. Now let's say this delay is more than what we would like, right? So what other option do we have? We can potentially increase the number of stages. Right? So the load we need to drive is something very large. Right? And we can add more stages here. Now, why does that help, adding more stages? I mean, already the stage efforts are matched, right? So now if I increase more stages, why do you think it will help? Can you tell me based on this equation? Right. So you have this parameter here, which is n times f raised to 1/n. If you increase n, this is going to decrease by 1/n, and it is also going to increase linearly. So there is a trade-off, but this means that there is some optimal value for this overall path effort. Right? So it is n into f raised to 1/n. So if you increase n in the initial stages, this 1/n is going to be the most dominating factor. So your delay will keep reducing. At some point, this linear relationship will begin to dominate, and then your delay can increase further. So there is an optimal value of n. If you simply put 100 gates there, doesn't mean you'll get minimum. So there is an optimal value of n, which we need to calculate. Quickly tell me what happens to parasitic delay if I increase n? How does it increase? It will also, so if I add n stages, it will be n times the parasitic delay of each stage I have added. Okay. Now, one last question. What should I add here? I mean, should I add inverter, buffers, or should I simply take a NAND gate or an OR2 and configure it as an inverter or a buffer? I have infinite possibilities, right? What gate should I use? Inverters, why? P is smallest one. Also, something else is also the smallest. G is also smallest. Right? So if you are adding any gate, the best solution is to add an inverter. So add as many inverters as you require. P is minimum, G is minimum. If you add any other gate here to achieve additional stages, you are going to pay a penalty, which is more delay than the inverter. Okay. Now, one last doubt you will have is, now I'm adding inverters. If I add odd number of inverters, your logic is changing. Right? Is that a concern? So whether it is a concern or not actually depends on the design itself. In a lot of cases, logical inversion is something you can easily correct. Either you can correct it here. I mean, either you choose that you need to have only even number of inverters, or maybe it can be corrected at the output. This is also driving something. So maybe after that, you can correct the logical inversion. This circuit might be able to take an inverted signal as the input, or it's also possible that you can correct it in the previous stage. So logical inversion may not be a problem in most applications because it's very easy to correct. So now what that optimal value of n is, we'll see in the next class. Right. So we'll calculate what the optimal value of n is, assuming it's an inverter, right? Now, if whether you want to, so the value of n you get, let's say this turned out to be odd, then you can choose to have the next higher end or a lower end. In most cases, what will happen is you'll get numbers like, let's say 8.2. So then you can choose whether you want to do 8 inverters or whether you want to do 9 inverters. Yeah, so I also want to add a small correction to a statement I made yesterday. This is about sharing of the diffusion, right? So far I've told you. Let's say you have 2 inverters. And if you wanted to add a contact, I mentioned that you have to place these, 2 transistors. If you want to add a contact, I mentioned that you have to place the transistor slightly away because of the constraints from the foundry, right? So I think this was true in a lot of earlier PDKs. But some of the PDKs I checked yesterday, you can potentially you can share the diffusion and still put a contact, right? So I could put these together and still have a contact here without causing a violation. So that is the, I think this was a question you also asked yesterday, right? If they are different sizes, then the diffusion sharing is not possible, right? If they are of the same size, then you can share the diffusion. So now let's say you have a connection like this, right? So it's possible that you share the diffusion of these 2 transistors. Then you can take a contact and then connect it to the next inverter. Next transistor. So like this. Now this is source, this is source. This is the source of both, this is drain. If they are of different sizes, then you will be dealing with something like this, right? And then let's say, this I'm pretty sure will cause a DRC violation. Layout rule violation this will cause. How do you define channel and all properly here? This is very asymmetric and no, this causes a violation. So quickly, let me ask you another question. What if you had 2 PMOSs on the top? Would you still be able to share the, okay, what if you had a PMOS and an NMOS? So far, this was not a question because your output was usually taken from here, right? Which meant that you are contacting. So I said that you had to place the transistors away and you had to count the capacitance twice. So now that if in a PDK, let's say it is possible that you can have a contactor diffusion which is shared. What do you think? Can I share these? Right? Let's say they are at the same size. Then is it possible to share? Right. So this is NMOS is basically you have N plus and N plus. Right? And for a PMOS, so you will have this in N well. And this is P plus and this is also P plus. So you can't share an N plus diffusion region with a P plus diffusion region. It will become a new device altogether. Okay. So now for this particular mid-semester exam, if you have shared a diffusion in this manner and then taken a contact out, I'll give you marks. And in general, for this course, we'll assume that we are working with a PDK where only uncontacted diffusion can be shared. Okay. And for the actual value, you will have to look at the PDK rules you're working. Thank you.